Hello. Remember that yesterday we have, if you remember, project number 2 is asking you to implement the same localization process you did solve in project number 1, but now using a better tool, which is the extended command filter. Then we are going to use the same source of information, but using a different approach. And you remember, we're trying to estimate the state of the system, which is for us the pose of the platform, X, Y, and phi. We want to combine different sources of information, some of them coming from sensors, some other is the state equation of our system. And we do know each of them is in a certain way lying a bit because they are polluted by uncertainty. Our model is not perfect, our nominal model, the kinematic model which we use. And in addition, the model has inputs, and our knowledge about the value of those inputs is coming through measurement from sensors. And those sensors, they do introduce noise. And then that affects our state equation. Also, the state equation sometimes doesn't capture the actual dynamic of the system. We do have other sources of information. For us are, for instance, the LiDAR. So the LiDAR is able to detect object of interest in our area of operation, and those are usually landmarks, which we did install for helping the navigation, for helping the localization of our robot or platform. So we could use that. Again, those measurements that we get from the LiDAR, they are coming with certain pollution. And in addition, when we do some processing, in our case, for extracting the center of the object of interest, we also introduce some error there, some disturbances. So all of these sources of information are good, but they are coming with error. And we want to consider those errors in a statistical way because we want to give more or less relevance to those sources of information, depending on the quality of those sources of information and also depending on how we are using those sources of information. This is what we want to do. And I also mentioned that information by itself, each source of information, they are usually incomplete. They don't allow us to infer what we want to infer, the state of the system. So you measure your certain object of interest in your local coordinate frame because you are processing the LiDAR scan. So that information is not enough to tell you what is your position on your orientation. In addition, that is coming polluted with certain uncertainty. So that is why we need to combine things. We want to do some sort of average, but we are doing the average between things which are not of the same nature. This is what I say here. We are trying to combine two different types of fruits. How to do that? Well, that is the mission we have using the extended command filter. So what is this process? Because this process is combining state equation and certain observation, which for us are measurement of certain output of the system. Remember, we measure certain output of the system, which are variables that happen to be function of the state of the system. They are giving information to us about the state of the system indirectly. We are not measuring the state of the system, but we are measuring certain variables which are function of the state of the system. So each time that we have the opportunity to measure an output of the system, we could implement an observation, which allow us to do a correction. That is what we did in the previous. But time goes, and we need to do prediction because we are estimating the state of the system at time t. 5 milliseconds later, we will be estimating the state of the system at time t plus certain sample rate that we have, suppose 5 milliseconds. So the system is changing due to the dynamic of the system. And for trying to predict that change, we use a prediction. And the prediction is exploiting our state equation, the nominal one, the one that we do have. So our process will be doing prediction and observation. Sometimes there will be no observation. Yes, sometimes it may happen that we don't have the opportunity to measure anything or to measure any variable that happen to be an output of the system. Sometimes we don't. And you saw this in project number 1. Yeah, sometimes it does happen. And because we are using a Gaussian estimation process in which the PDF, that is the statistical representation we have about the state of the system, that PDF is Gaussian, and due to that, we could maintain that PDF using two parameters, the expected value and the covariant metric. They tell us everything about that PDF. We don't need to be representing that PDF using a function or a numerical representation of that function. We just need this couple of parameters. the expected value of the state vector and the covariant metric. That is what we need. And we do remember that from when we discuss about the Gaussian representation. And then we need to initialize our process because this process, estimation process, that does start at a certain time. So that is the initial time. Time 0, you want to talk. We are talking here in terms of discrete time. So we need to have an initial expected value, an initial covariant. If we do know very well our initial condition, that is the case that we are having in project number 2, because the data set which we are using for playing back, repeating the experiment, that one is telling us with certainty that was the initial pose. Okay. Suppose that is the situation. So we have an expected value. There's going to be x, y, and phi at time 0. That is the expected value. Now, how confident we are about this initial expected value? If we are fully confident because we believe that is perfectly accurate, so our covariant metric, which is going to be 3 by 3 because our state vector is 3 by 1, is going to be plenty of zeros. Yeah, because we have full certainty. By the way, these diagonal elements are the variance of the marginal PDF about this, and this variable. Yeah, so that is telling us that our marginal PDF about the initial position component X has a standard deviation 0, and the same for the other, and the same for the other. So we have full certainty. So, and this is what we are saying here. And if someone tells us, oh, your initial pose was 0, 0, 90 degrees, and you are working in this case in radian, I put this pi divided by 2, okay? That it will be my expected value of the initial pose of the system. And what about the covariant? Will be 0 because you told me that is perfect. Good. What happens if we are not completely sure about that? They tell you, oh, yes, the position should be x equal to 1. Sorry, x equal to whatever value I put here, 0, 0, and 90 degrees. But we are not sure about those values. So we believe that the standard deviation will be 1 meter for x, 1 meter for y, and 10 degrees for the heading, because we don't know perfectly that initial position. So in that case, you're going to indicate that in the covariant metric. That is why I'm including here standard deviation 1, standard deviation 1, and standard deviation 10 for each of the marginal component of this covariant metric. I put the square because these are the variance. We do have that. But suppose you want to place a bit safer. I done maybe it's a bit more, and then you decide to multiply by 2, which is equivalent to multiplying each of the initial standard deviation, in this case by square root of 2, about 50% more. Why do you have zeros here? Because I know that there is no statistical dependency in my uncertainty about representing x, y, and phi. So they are sort of independent. So this is why my covariant metric is perfectly diagonal. Okay, now you need to have a prediction. Yes, I need to apply the prediction. Now, what do we need? I need to have a nominal state equation or a nominal process model or whatever name you want to use for that. State equation and process model are the same for us. Yes, I do have that thing. So if you ask me to implement the prediction and get the new expected value, to predict what is going to be the expected value one step ahead or from the past to now, I'm working suppose in discrete time here, and that corresponds to 5 millisecond sample rate. Okay, I jump 5 milliseconds to the future or from 5 milliseconds in the past to the present. And then I apply this equation, the nominal state equation, for obtaining the new expected value. That was what I had before, and that corresponds to the expected value, our prediction about the state of the system one sample time later. And I also using here what I do know about the input of the system. What do I know? Oh, this is the value. This is what I measure from the input of the system. Okay, I use that. That is the best that I could do for providing the prediction of the expected value. By the way, this is what you were doing in project number 1, because you were doing just this. But in project number 2, or in general, for when you have a Kalman filter, you will be also maintaining the covariant metric. And for that, we need to do the same that we did for whatever transformation we apply in tutorial in week 7. Yes, I have my previous covariant metric, and I need to apply this multiplication on the right and on the left using the Jacobian of the state equation respect to x, evaluating that Jacobian at the point of operation for me, which is my current expected value and my current expected input, which are the measurement that I'm getting. The expecting value of the input is what I measure. I do know they are sort of wrong and they follow some Gaussian distribution, but for me, that is my expectation about the measurement happening now. So this Jacobian, which I call Jake, after evaluating that analytical expression in current expected values and the current measurement of the input, that will be a metric Jake. Yeah, which will be square, and it's going to allow me to obtain the new covariant after applying the model. And in addition, I'm adding this covariant metric, which is the covariant metric of the uncertainty, which is polluting my state equation. And one step, because this is talking about what happened at just one step. We continue with this discussion and say, well, what is exactly our model? Well, my model in my state equation is my kinematic model, the one that we are using, the one that we did use in project number 1. This is my kinematic model. These are my input, and this is my state vector, and this is my equation, my state equation. I expressing this in discrete time k, but that corresponds to our small delta t when we are talking about continuous time t. All right. And then could you get the Jacobian metric of this state equation respect to the state vector? Yes, I need to do the partial derivative. And this is my equation now. Okay, I put this in just talking about x, y, and phi, and also the input, no mentioning k here to facilitate our partial derivative. So this is the first component. The second, okay, I need to get the partial derivative of this respect to x, y, and phi, and the same for this, and the same for this. And this is the Jacobian that I got, the partial derivative of the first component of the state equation respect to x, respect to y, and respect to phi. The second component respect to x, respect to y, respect to phi. And finally, for the last component, which is describing the evolution of the heading, yeah, respect to x, respect to y, respect to phi. And you see that this partial derivative, they do correspond to this state equation. Okay, good. I'm not going to explain what is this partial derivative in particular because you know this from mathematics. That is the analytical expression of the Jacobian of the state of the equation respect to the state vector x, y, and phi. What about the Q metric, you say now? How do we get that? Well, we need to analyze the source of uncertainty in our state equation. Who are here the main contribution to the error in our state equation? One of the main contributors to the error in our state equation is the noise polluting the input of the system. Because remember, we are getting those from measurement coming from the gyroscope, measuring the angular rate, and from the angular velocity sensor, the speed meter. And they are introducing error. We do know that those errors are Gaussian. Why Gaussian noise? Yeah. And we do know approximately the variance of each of them. That is good information for us. All right, so we model here, which this is the noise polluting my input vector. We don't need to repeat this explanation. I'm doing this just once. You are going to apply a procedure which is systematic. You don't need to be reinventing then the wheel again about this, saying, the input are polluted with certain uncertainty. But we repeat this here. So these are our input vector, which is 2 by 1, longitudinal velocity and angular rate, heading rate more exactly. Okay, and this is coming with this, just adding to this vector. And we want to know, and we know that this will produce an effect equivalent, which is here. It's going to produce, it will be like the nominal model, or in this case, we say this is the nominal model, plus certain disturbance here, certain discrepancy. And who is this? Well, this is just the effect of this. And because this is having usually not a large amplitude, so we could apply linearization to capture this small fluctuation here, how it's going to be affecting the result. So that could be done just getting the Jacobian of this function respect to this perturbation here. But because it's just adding to this input, we just get the Jacobian of this function respect to the input. It's going to be the same thing. And we are going to evaluate that thing at the point of operation now. So what is this JQ? This is the partial derivative of my state equation respect to the input vector. And we are going to do the evaluation at the current value of the expected value of the state vector and the current value of the input which we measure. Those are numbers. So we're going to get the analytical expression of this. So we're going to replace this by this instant of the state vector and the input vector, and there will be numbers, and it will produce a metric with numbers. There will be a metric with numbers, and we are going to obtain the covariant of this equivalent noise, which is going to be Ju multiply the covariant of the original noise here, affecting the input. And we get this because we are doing the same that we did in tutorial number 7, the same thing. We are talking about the transformation of a random variable, in this case, a nonlinear transformation, and then we get that. Okay, so how is that in our particular case? Well, this is my state equation. I should use this because it's easier to appreciate this one. And I'm going to do the partial derivative of this first component respect to one of the input and the other input, yeah? And I'm going to do the same for the second component of the state equation and for the third component of the state equation. If I do that, I will get this metric with the partial derivative of each of the components respect to each of the inputs. And the input are 2, so this is going to be a metric which is 3 by 2, because I'm getting the partial derivative of a function which has 3 components respect to argument, which has, in this case, I'm talking about the input, just the input vector, which has 2 components. So I'm going to get the partial derivative of this respect to the first component of the input vector, which is the velocity, the longitudinal velocity, and the partial derivative respect to the heading rate. It's going to be this. It's 0, this one, because there is no participation of the heading rate here. The same happened here. And in the last one, there is no participation of the longitudinal velocity, but it does have participation of the angular rate. And this is why I do have this Jacobian metric of the state equation respect to the input vector. Yeah. This is the full equation. It's x plus this, y plus this, phi plus this. Okay. We do have this JQ, and it's an analytical expression which we are going to evaluate at the current expected value of the state vector and expected measurement or measurement that we got. But because this analytical expression involves only the participation of the heading variable, so we just need to use the expected value of the heading at this very time at which we are calculating this JQ metric. If we want to spread this more in a strict way, yes, I need to replace here the expected value of the heading at this current time before we do the prediction, which is this, my current expected value. Everything is in place here. We do have that. And then you say, well, but we need to know the covariant of the noise which is polluting the inputs. Well, that is something that we do usually have, because we do experiment with the sensor, because we read the specification of the maker, and we do know that. So we do know how good is the speed sensor and how good is the heading rate sensor, the gyroscope. Suppose in this case that we do know that because we did experiment, when we are moving and traveling, usually the speed sensor introduces an error of 1 centimeter per, okay, because we are measuring speed. So suppose this is in centimeter, it's meter per second, okay? And I say 1 centimeter per meter, no, 1 centimeter per second, okay? So, and then we say, okay, that will be 0.01 meter per second, yeah? And I'm going to spread this I'm expressing this in meter per second because I'm using meter per second in my implementation. But the maker told me 1 centimeter per second. And also they tell us the gyroscope introduces a random noise, which is Y Gaussian noise as well. And it has a standard deviation of 0.5, half a degree. Okay. And then I'm going to get the variance of that because I need to put this in my covariant metric of the noise polluting the input measurement. And because I'm using, in my case, radian, I'm going to convert to radian. So I convert this to radian and I got the variance, this marginal variance. And that's it. This is my covariant metric of the noise polluting the input measurement. And it's diagonal, not having this non-diagonal element equal to 0 because it happened to be that the noise which is polluting one sensor and the one that is polluting the other sensor, they don't have any connection between them. Statistically, they are independent. Those noises are independent. That is why this covariant metric will be diagonal. So I do have everything because I have JU, because I do calculate this at each prediction. And I also have this, which is a constant. This is changing. That depends on the time. More exactly, depend on the current expected value of the heading in our particular case. And this is a constant metric, which is this, that is defining the quality of our sensors. And we have everything. Yeah. And you may ask, that is the only source of uncertainty for my model? Well, there was this particular effect due to the noise polluting our measurement of the input, but also there could be other errors in our model, not due to the noise polluting the input. It could be because the model is lying by itself. May that situation happen? It does happen in certain cases. It doesn't happen in our particular case because the machine was moving slowly and the terrain was good, perfectly two-dimensional, everything was beautiful. So there was no skidding, there was nothing failing in the traction of our machine, but in a real application, when you are really dealing with that terrain, which is more complicated, or the machine is moving now, suffering high, intense acceleration, and it's skidding, then you will need to consider that. You will need to get a statistic about how are those uncertainties. In our case, it doesn't happen. But in general, keep this in mind. There are many sources of uncertainty affecting our state equation. So I here specify that thing. So we will have an additional noise, the one that we had due to the input uncertainty affecting the input, and also this extra component of uncertainty due to the failure of our model in certain condition. So if they told me, oh, usually when we do this, applying this system, I got this indication that after moving, suppose for 1 meter, introduce about 3 centimeter error in position X, in position Y. Oh, okay. And then I could say, okay, what is going to happen in average in just one sample time? If this was 5 milliseconds, it will be 0.05, yeah, 0.005. And then multiply this by that average of error that happened in 1 second to have an idea how wrong could be this thing. Just to tell my model, watch out, you are not perfect. You are introducing small error in average. And then you could do this. Again, it's diagonal because there is no interaction between one and the other component. And if I suspect there is nothing issue about the heading, well, no, there should be no issue because I'm capturing this, integrating the angular rate, so there should not be error there. So there is no contribution here of covariant adding to the component 3,3 of my covariant metric, so it's going to be 0 here. That is possible to consider. So then the total covariant will be the contribution of both sources of noise. And because you know from our discussion before, when you are adding two random variables which are Gaussian, so the resulting will be a new Gaussian value whose expected value will be equal to the addition of the expected value. In this case, it's going to be 0 because we are assuming both sources of noises are Y Gaussian noise and they have expected value 0. But they do have covariance, and then I do the addition of the covariance. And that will be the total covariance, which I should include in my prediction step. Okay, this is what it's saying this. That is not our problem in our project number. What happened with the update? Well, we are going to use the extended Kalman filter update because our system is nonlinear. And if you remember, the extended Kalman filter update had this expression, which we don't need to remember and we don't need to memorize, but we do need to apply this, and we do need to know how to apply this. What is the information we need to feed to this update? Well, I need to feed the measurement itself. Whatever we measure, we need to feed that thing. It's going to be a value, which is going to be the measurement which is polluted with certain uncertainty. Where do we tell this Kalman filter update about the quality of this thing, or the covariant more exactly, of the noise affecting this measurement? Well, it's in the R metric. We need to provide that. Usually we do know, because we do know how wrong could be our sensor when it's measuring. Good. What are the participations? Here we have this H. What is this? Is the output equation. Our output equation is H of X. In the linear case, we'll remember capital H multiplying X. the output metric multiplying the state vector. But in our case, it's a nonlinear expression. It's going to be h of x. So here we are doing an evaluation with this value. This is the expected value of the state vector, our prior expected value, because this is the expected value of the PDF, which is the prior, the one that we have before we do the update. So we apply the output equation, and that produced the expected output variable. Okay, and we compare this with the measurement of the output variable. And you could be sure both are lying a bit, because this measurement is coming with certain pollution due to the noise coming from the sensor. And this one is also lying a bit, because that it will be the hypothetical output variable if the state of the system were our expected value about the state of the system, but our expected value about the state of the system is not perfect anyway. So we get a discrepancy here, this set. And this set, the name of this is usually the innovation. Yeah, the innovation is telling us the discrepancy between the actual measurement and the expected measurement. All right. What else do we need in this expression, the H, capital H metric? What is that? Is the Jacobian of the output equation respect to the state vector. Evaluating that Jacobian at the current expected value of the state vector. So this will produce a metric for numbers. This is an analytical expression. It's a metric with numbers. Okay, good. And H is going to participate on all this operation, in which is very important to see we have the participation of this, the covariance of the noise polluting our measurement. Yeah. Also the participation of the prior covariance metric. Yes. And H, of course, which is capturing the structure of the output equation. But because it's non-linear, we are linearizing using this Jacobian at this point of operation and the current expected value. Good. That is the best place for linearizing for us, because that is, we believe, very close to the actual value of the state vector. All right, so we have this expression here, and what is going to produce this finally is going to produce the new expected value and the new covariance metric, the posterior. They are talking about the same state vector. It's talking about the state vector at time k+1. But they are exploiting the information that we got from this measurement. So we had this prior expected value and prior covariance metric, which also they were talking about the same variable, the state vector at time k+1, but they did not use any information from the current measurement. That is why we said they are the prior, and then we apply this thing and we got the posterior. And this is the definition of the Kalman filter update, which we do know from the previous lecture. The important thing, we had to provide this, the measurement that we just got from the sensor. We need to exploit the prior expected value. We need to exploit the output equation that we know, our nominal output equation. We need to calculate, or we did calculate this before, the analytical expression, the Jacobian metric of the output equation respect to the state vector. We do this just once. We get the analytical expression and we just do the evaluation on the current expected value of the state vector. That is the H, which is participating in all this operation here. And we do know the quality of our sensor. This is the covariance describing the characteristic of the noise polluting our measurement of the output variable. All right, everything is here. Our intention is to get these two parameters, which define the posterior PDF about the state of the system. All right, we continue with more. This is repeating the same that I did. This is our data, and this is our result. Good. How is it going to be implementation? Well, I did mention this before in some previous lecture, but we could have a function like this one. Do update. Give me the current covariance, the current expected value, tell me the H metric, because you are doing the linearization outside of this. I don't know here, say the function, I don't know your output equation. So you get the Jacobian analytically, you do the evaluation of the current expected value, and just give me the H metric. This is what is telling you this function. Also tell me the R metric. You tell me that thing. And also give me the innovation. You do the comparison between the measurement and the expected measurement. So do that thing, send me all this data to me, I will do this operation, and I will produce the new expected value and the new covariant. This is completely general, could be for anything, because you are calculating the H metric and the innovation outside of this function. Okay, that's it. That will do the update. Now, this is in general terms. How would it be for my particular case? Because what I'm happening to me is I have this LiDAR measuring the position of certain objects of interest in the LiDAR coordinate frame. And I do know that objects of interest correspond to certain landmark whose position I do know in the global coordinate frame. So I want to exploit that. In this equation that I'm obtaining here, I'm assuming that this LiDAR is actually here. There is no displacement. This is what I put here. Attention, this observation model assumes that the LiDAR is not displaced, okay? Let's assume that for simplifying our discussion here. If the LiDAR were here, so in that case, the distance between the center of the LiDAR, that in that case will be a 0, 0 of the car coordinate frame, so that range will be the distance between my position X and Y, that is the position of my LiDAR or the position of my car. They're exactly the same in this case because there is no displacement in the global coordinate frame. Respect to the position of the landmark in the also global coordinate frame, which correspond to the same distance that happened in the local coordinate frame. Because now I'm 0, 0, and this object of interest is being expressed, represented, or detected in my car coordinate frame. So I have the position of this object of interest in my car coordinate frame, so that this distance corresponds to the same distance, or the distance between my position and the position of the object of interest in global coordinate frame. And because I do know that that object of interest corresponds to certain landmark, I'm going to exploit that. So these are the equation now, the output equation, which are talking about my state vector, because they are function of the state vector. My state vector, remember, is the position and orientation of my platform in the global coordinate frame. So here is X and Y. So this just, and this is the position of the landmark in the global coordinate frame. That is data, it's in the map, it's provided to us. The only unknown is X and Y. And phi, of course. If we also consider this relative angle, or the angle that in which appear this object of interest in my local coordinate frame, in polar, I could get also an expression here, which involves also phi. But in project number 2, A1, we don't request you to analyze this alpha. We are just assuming that we have the range because we are pretending that we have a sonar, or because we are assuming that it's similar to a GPS in which we just measure distance to the object of interest. Yeah. I did that thing for simplifying your implementation. Of course, if we exploit all this information, will be better than just exploiting this distance. But at the moment, we assume that. And then we say, okay, what happened in our project in part A1? Well, okay, your observation function or your output equation will be this, which is perfectly talking about the state of the system and some variable which we do measure, which is going to be the distance between the sensor, the LiDAR sensor, and the position of the object of interest. And I repeat, because now we are assuming that this thing is here exactly at 0, 0 of our car. So this is perfectly correct. Yes, if you had this thing with certain displacement, this equation will change. You are trying to represent X and Y position of the car in the global coordinate frame using that convention in which we are modeling this point of the car. Good. All right. So then, assuming that that is the output equation, how would be my Jacobian metric, the analytical expression? Well, suppose the case in which we are having range and bearing, also the angle. Okay. So, well, I need to get the partial derivative of this respect to X, Y, and phi, and the same for this second component. So this is what I'm doing here. Partial derivative with respect to X, Y, and phi of the first component, and the same for the second component, which correspond to be this. You could obtain this using the chain rule. The derivative of this square root of certain argument, and also the derivative of the argument with respect to X, Y, and phi, which is going to be this. And it's going to be 0 here, the third column, because this one is clearly not function of phi. Yeah, so 0. If we were in Also processing this measurement, alpha, we will get also the partial derivative of that for obtaining the second component of this Jacobian. This Jacobian in this case, because the output equation has two components and it's function of three components, x, y, and phi, is a metric which is 2 by 3. If we are just talking about this, so that our output equation is a scalar, this H metric will be 1 by 3. By the way, this is what you have to do in A1. Okay, good. And then you ask me, what about R? In this case, I'm measuring two channels, range and angle, or bearing, alpha. Okay, if someone tell me, you know, according to the calculation that we do, the noise that is introduced in the LiDAR and all the issues that are affecting our calculation of the center of the object of interest, we know that the distance that we are calculating is 10 centimeters, usually that uncertainty, that standard deviation. It's white Gaussian noise, it's completely random, and it's white as well. And it's Gaussian, and it has a standard deviation of 10 centimeters. And because I'm using here my calculation in meter, I put here the standard deviation 0.1. And because this is a covariant metric, and this diagonal element corresponds to the variance, talking about that particular component, component number 1, which for me happened to be the range, measurement, the range variable. And because talking about the measurement, the noise polluting the measurement, this will be 0.1 square, the variance. And if they tell me that the uncertainty polluting the angular measurement alpha is 2 degrees, I will do that thing the same. There will be the standard deviation, 2 degrees. And because in my case, I'm working in radian, I convert to radian, and this is what I get. My marginal variance, talking about the noise polluting the measurement of alpha. Yeah. And then you ask me, what would happen if we have more than one object of interest? We have 3. How could we do? You could process all of them simultaneously. I'm not going to tell you how to do that because I recommend you to just apply a sequential approach, because we do assume the noises which are polluting those measurement of range and angle alpha, they are white Gaussian noise. We could process those observations individually, one after the other. So what we are going to do is, you have 3 objects of interest, each of them providing here a range. You are going to apply the Kalman filter update for the first range. That will produce a posterior, because you have a prior, which is your current expected value on covariant metric. You will apply that update for that scalar measurement in the range. And in that case, this will be just R will be a 1 by 1 metric, a scalar. It will be just this, 0.1 square. I do the update, and that will produce a posterior. But that is not the final posterior in this LiDAR event, because I have another 2 objects of interest. So you will repeat that thing using the posterior that we got in the first iteration. We apply this as a prior in the second iteration in this sequence of updates. And that will produce a new posterior. And then you process the last one, the last object of interest, the last measurement of distance to that object of interest, having this prior, which was the posterior that I got in the previous calculation. And now we do again one Kalman filter update, and we get a new posterior that will be the final posterior in this combined update, processing multiple objects of interest. This is what you would do for solving the problem. That is perfectly consistent with the theory of the Bayesian estimation, in which we are multiplying likelihood, because each of the likelihood function correspond to piece of information which is being polluted by certain source of uncertainty, and this source of uncertainty polluting each of these sources of information. Those sources of uncertainty are independent. We say that they are white noise. Yeah. In our case, they are white Gaussian noise. All right. And that is what we needed to do for understanding this particular problem, which is localizing our platform, exploiting the LiDAR information, pretending that we have a sonar. So we just process distance to the object of interest we are extracting. And also we are exploiting the kinematic model using as input measurement we got from sensors, but we also consider that those sensors are introducing error. And we are going to see a demo, but that corresponds to a different video. We are going to stop this now, continue later.